Now, this is a very interesting I would say formulation for getting the power in forward flight, which we saw because we know that power is only main rotor power. Let us not bother about the tail rotor. Main rotor power is q times omega. Omega is the rotor RPM. Now, we know earlier Cp is equal to Cq. So, I directly go and then calculate torque coefficient for the main rotor. The torque coefficient is nothing but the yaw moment torque divided by that non-dimensional quantity. So, we write our Cq as Q, which is actually mz. Please note that this is the z component of the moment. Okay, last class I wrote that. So, rho into r. Now, last class I wrote, let us take 0 to capital R, n is the number of blades, we are taking mean value. I will not put that 0 to 2 pi and 1 by 2 pi, it is assumed that we are doing that. Okay. Now, this is we wrote R f, right. If you look back your notes, last class I wrote this, moment mz is this, because the drag force into the radial distance, and you divide by again rho okay, and we can non-dimensionalize. So, I will write this Cq is n okay, u r square. I am putting this, I will tell you how I got this. This quantity I divide by r, capital R, so multiply by that goes there. So, this is r bar and this is also non-dimensionalized to dr bar, that is why I will get r square. Okay. R bar is r over r, okay, and I multiply C just for, and you know f y 1 which is given from the earlier expression, that we will write it later. This is, you can now take n C r over pi r square, that is sigma, solidity ratio. So, you will write sigma into 1 r you will put, okay, rho, okay, cancel out this and you will have only this term. Okay. So, this is sigma rho omega r whole square card in the denominator. Now, let us write our f y 1. We had defined earlier f y 1, if you go back, that is nothing but the drag force. Okay. Look at your notes, it is essentially, where is your f y 1, yeah, f y 1 is minus L sin phi plus d cos phi. Okay. and you know lift you have written as half rho u square C CL sin phi plus C d 0 cosine phi. Okay. But what we will do is we will substitute this term directly here, but the minus sign essentially represents that the torque is in the clockwise direction. Okay. So, since we are calculating power, so it does not matter the sign we will throw away. So, we will not be carrying on this sign completely, sign does not matter, it is only to say that this is the quantity, because if the rotor is rotating counterclockwise, my torque is clockwise, that is all. So, I am getting the torque coefficient as a magnitude, because that is basically the power coefficient. So, the minus sign is we are throwing it out. Now, let us go back here and substitute this expression. So, you will get C q becomes essentially sigma rho C omega r whole square C L sin phi plus C d 0 cosine phi r bar d r bar. Okay. I have put this here. Now, is the small jugglery we will do. See, we know f y 1 is this. Similarly, we have f z 1 is essentially that L cosine phi minus d sin phi. Okay. You are going to replace the L by f z 1. In other words, you substitute here that half rho u square C, this will be C L cosine phi minus C d 0 sin phi. Write C L in terms of the rest of the quantities, you will get C L. Okay, let me put it C L into sin phi. Okay. I am multiplying by, so divide by cosine phi. So, you will have f z 1 over half rho u square C, that is this term, into sin phi cosine phi plus C d 0 sin square phi over, please note this I am getting it from this equation. Sin phi is just I am multiplying, because I need to substitute this right here. Okay. This is just a jugglery, that is all, mathematics. I am not making any approximation here, that is why this is a little tricky derivation. Okay. Now, what happens is when I substitute this expression here, I will put what will happen, that is C q will become sigma, let me write the whole thing, sigma over, let us write C, okay, 0 to 1 half rho u square C is there divided by rho omega r whole square. Okay. Is it correct? Huh? Yeah, rho omega r square half rho is, and I am going to substitute for CL sin phi this entire expression Fz1 over half u square c sin phi over cos phi plus this is CD naught sin square phi by cosine phi plus CD naught cosine phi into dr bar, sorry, r bar dr bar, okay, r bar dr bar. Now, if I club these two terms, this will become CD naught over cosine phi. Okay. So, let us, so your CQ will become sigma over C half rho u square C over half rho u square C, this is tan phi plus CD 0 cosine, okay. And you know from our flow tan phi is UP over UT, or you may also write it as UP bar over UT bar, okay. And cosine phi will be over U. This is the total velocity u bar, okay. You can directly take this substitute here, and it will be kept in one particular form, okay. After that, what is done is, let me erase this part because this is not required now. I just leave it at that stage and get back to another expression, which is, if I put all of them, because you know that this term gets cancelled with this term, okay. You will have 1 over rho. So, I can, maybe I will write this, that is better. Let me, okay. You can put it UP over UT, or you can put the bar also, there is nothing wrong. And then here this will become half rho u square C, right, and u bar over UT bar C D 0 r bar d r bar, okay. This is, you can put a bar, it does not make any, finally you will find that it will get nicely cancelled, it will come into a nice clean form. Now, this is the torque. If you see, it has two components, one is due to the profile drag CD naught, another one is due to the thrust part, okay. Now, similarly we will formulate another expression in terms of the that horizontal force, which is CH, horizontal force. CH is basically H over pi r square omega r whole square. This is again number of blades. You go back, look at the whole thing, it will be 0 to 1, sorry, 0 to r, f y1 with a minus sign, sin psi plus f x1 into dr, okay. you know Fy1, Fx1, please understand, because Fx1 is Fy1 we wrote earlier, that is minus half rho u square c Cl, what Cl sin phi plus Cd 0 cosine phi. Okay. And your Fx1, if you look at it, Fx1, that is minus beta Fz1 earlier. Okay. All right. What you do is you take these two expressions, put them here. Again you do the non-dimensional, that r bar 1 r will come. Okay. Now you will get the CH expression sigma over C 0 to 1, because I am just saying you put this here, okay, and this also there, put it there. What you will have after NC pi r, you write it in terms of sigma, okay, that is solidity ratio, NC r over pi r square, okay, and you will get 1 over rho omega r whole square half rho u square c, open up a bracket, I am writing f z 1 over half rho u square c tan phi plus C d 0 into 1 over cosine phi sin psi minus f z 1 beta cosine psi d r bar. So, please note that what I have done, I have substituted this expression there, okay. After that for Cl I substituted from here in terms of Fz1, that is why it becomes Cd not 1 over cosine phi, you follow, and this is in terms of Fz1, okay. It is a two step. So, I am writing my CH, erase this part also, okay. So, this is my entire expression for, okay, CH. Now comes you can substitute here, simplify, let me simplify the whole expression here. This becomes CH is sigma over C 0 to 1 over rho omega r whole square. What you do is you take the Fz terms, okay. You will have, this is tan phi is up over ut, okay. This will cancel with this. So, Fz1 up over ut sin psi minus Fz1 beta cosine psi, okay. So, you will have two terms. I am going to write only the up over ut, this is this sin psi this is minus beta cosine psi, okay. You take it f z 1. Maybe this bracket is not necessary, I do not think I need this, okay. Yeah.
Each expression there was this CL sin phi plus CD naught cos phi.
Yeah, I am substituting for CL.
But where is CD naught cos phi?
That will add with the other CD naught, FZ1. Yeah, you will have FZ1. See, FY1 has a CD, okay, that will combine, leaving you in this similar fashion, identical to this, okay. After that, this you will have plus 1 over rho omega r, that is this term, you have to take this term, okay, half rho u square, you will have u bar by u t bar, this is cosine phi, and you will have a card, then there is a CD 0 and sin psi, and this entire thing is bracketed dr bar, okay. Is it okay? Because this is the term, I am taking half rho u square c, cosine phi, that is given ut by u, that is what is coming here, and then there is a CD naught, there is a sin psi, that is what here CD naught sin psi, and this is the remaining expression, okay. Now you have written two expressions, one for CQ, one for CH. You know CH is the force coefficient, longitudinal force coefficient, CQ is the torque coefficient. Now only some little more, I erase this part, okay, because now some algebra is done. You write your CQ has two components, one due to induced, another due to profile. I is induced, 0 is profile, okay. Now what you do is similarly you have CH also induced, that is FZ, and there is a profile C. You add and subtract mu times C H 0 plus mu times C H I minus basically mu C H, because C H is this entire thing. I am writing this term as C H 0, sorry C H I, this term as C H 0. Same thing here, this term as C Q 0, sorry C Q I, that is C Q 0. And then I am just like you add and you subtract, because basically C H is C H naught plus C H I, okay. It is kept in this fashion. Now what is done is they calculate these two, you add these two terms, okay. That is CQI plus mu CHI, you understand. Then CQ naught mu CH naught, like that you combine the terms, okay. When you combine, if you write CQI plus mu CHI, let me go back and then possibly maybe I will use this, yeah, okay. So, we will have CQI plus mu CHI. This is sigma over C 1 rho omega r whole square r bar up ut, or you can write up bar by ut bar. So, you will have r bar up bar over ut bar, it does not matter, bar you can keep it, then plus I have to take this term, okay, that is up bar over ut bar sine, but is there a mu is there. So, I will put a mu, then minus mu beta cosine psi d, and fz1 is there, sorry, fz1 dr bar, fz1, right, fz1 dr bar. Now, you look at this term, if you go back to your notes, you will see ut was defined as omega r ut bar, okay, which we wrote as r bar plus mu. Similarly, up as omega r up bar, which is omega r into lambda plus r bar beta dot plus mu beta cosine psi, right. What you do is you substitute here, because ut is common, right. What is ut bar? R bar plus mu sin psi, because between these two terms, okay, this term is nothing but up bar, up bar is here, up bar minus mu beta sin cosine psi, that will go off. So, leaving behind your CQI plus mu CHI is nothing but sigma over C 1 over rho omega r whole square lambda plus r bar beta dot fz 1 dr bar. Okay. Now, here something is done, that is, if you take this term, there is a force r beta dot is the velocity at that point, and which can be written as r beta divided by, because you can convert d beta by d psi, okay. And this, if you do averaging over one revolution, the work done by this force, because this is a periodic motion you are assuming, okay. But here there is a nice explanation, but for that you need to know the blade flap equation, okay, which I will be deriving later. Usually the flap equation, I am just writing it here for your okay, you let us just write for, just for this is the flap equation. It is a general flap equation let us assume that it is a rigid blade, whatever we made, some hinge offset, everything. Flap equation will usually be, which we will be deriving later, but I am just writing it here, some into some gamma, which is again one more number, r bar f z 1 over a c 1. Gamma is some non-dimensional number, r bar f z 1 dr bar, okay, into a is the lift curve slope card. These are all, you can take it as constants, you can take it out. This is my flap equation. One way of writing it is, what people do is, this is also 0 to 1 r bar f z 1 dr bar, okay, r bar f z 1 dr bar. So, this nu square is some, is a frequency term. You can substitute this term only for this and then you integrate. That means, everything is converted into basically beta double dot into beta dot and then nu square beta beta dot, something will come, and integral, of course, that you have to do over one cycle. When you do one cycle, what happens is the aerodynamic force, this is basically the aerodynamic force, this particular side is the inertia term, okay. The aerodynamic force, because dynamical equations, what you do is external force and centrifugal force is also there, that is why this is the inertia term, I said. When you do that, since you assume periodic motion, you will find that the total work done by this force in going around this is 0, okay. Therefore, the proof, if you want, you have to substitute this here and then get it. I will show that that quantity has to be identically 0. So, the CQI plus mu CHI will simply become lambda fz1 dr bar, okay. I will first because the lack of space, I see if I do this part, I do not know where to erase it, okay, let me erase this, okay, and because I will just show that, because this is a very interesting thing, that is how, because these are all practically valid. I am writing this, I am taking average integral 0 to 1 r beta dot f z over a c d r bar d psi, okay. This is what I need, okay, r bar beta dot f z dr, and a c is because when you take the non-dimensional, it will come that factor. This is nothing but, this is equal to, you go to this equation, this will be 2 pi, I am taking beta dot 0 to 2 pi, then I am doing 0 to 1, this is r bar f z a c dr bar. I just take a gamma and divide. So, I will put, this is beta double dot nu beta square, sorry, nu beta over gamma, here what, some d, there is no d, d psi. Is there a 0? No, no 0 to 1, I am sorry. Okay, because there is no 0 to 1, because this is 0 to 2 pi, that 0 to 1 r bar f z 1 a c dr bar, that is written by this, replaced by this. So, you have essentially 1 over 2 pi 0 to 2 pi beta dot gamma is there, gamma is another constant which we will define later, beta double dot plus nu beta d psi. Okay. This particular term, maybe I erase here again, I will write it. This particular term can be written as d by d because dot is nothing but d by d psi, non-dimensional time derivative. This will be plus, so there is a square, okay, nu square beta square d psi. Okay. And since this will go off, that means differential of some quantity which I am integrating from 0 to 2 pi, and this quantity okay, this is a velocity square, this is position deformation square, this is like a kinetic energy and this is like a strain energy position square. We will later you will know that this is what it is, and it is 0 to 2 pi means I will get what 0 2 pi, and it is periodic motion. When it is periodic motion, that means what you start, you come back to the same point. Okay. Therefore, this entire thing will be 0. So, it is essentially the work done by that term, that r bar beta dot is identically 0 term. Okay. Therefore, your CQI mu CH, it will become a very neat simple expression. Oh, there is a factor 2 here, you can take it. Okay, there is a 2 you take, sorry. Okay. Yeah, because 2 times you can put a 2 factor 2 because this is a d by d square. So, 2 beta dot beta double dot. So, the factor 2 cancels out. So, essentially I can now write my CQI CHI in this fashion. Okay. Lambda FZ1 dr bar CQI mu CHI. Now, if you look at this particular term CQI plus mu CHI, which is sigma over C lambda okay. Let us take this sigma is what NC by pi r NCR pi r square, you take it like that. So, let me put it this way 0 to 1, I will take the C also inside. Okay. So, N C R pi r square into C rho omega r whole square, and you have FZ1 lambda dr bar. Dr bar is dr over r, right? Dr bar is dr over r. Now, N C you cancel out, this r you cancel out. Okay. You will have N FZ1, FZ1 is Fg1 dr is what? This is the force per small, Fg1 is force per unit length into dr is that force divided by rho pi r square omega r square. This is basically non-dimensional which we use for thrust. N is the number of blades, right. So, this particular term is written as lambda d c t differential. This is a differential force only, small elemental force, okay. And this is done. If you want to do, you have to do an averaging over the 2 pi, that is why that averaging is always included, but this is over the full disk, because you have to do the full disk, because if you average, y averages over the entire disk 1 over 2 pi, it is always there. So, dct, because we mentioned earlier Ct at every time it is varying, but when you do the averaging you get the mean value of the thrust, okay. And this is basically the average value of the thrust, but differential element, and lambda is the inflow through the disk at that location. So, it is like the entire disk is, you can split it into small rings. It is like you take the whole disk, make them small, okay, like we did thrust, and you know lambda, it is like a weighted thrust, but later if lambda is constant, this will come out, right, and this is nothing but thrust coefficient, okay. That is what we will use after reduction. Now, if we go back to our formulation of CQ, the complete, because we said the power coefficient Cp is nothing but Cq, which we got it as one of the terms lambda dct. This is the mean, this is an average value, plus you have CQ0 plus mu CH0 minus mu, it is there, okay. This term is still there, because this is only CQI mu CHI. Let us now take only CQ0 mu CH0 term now. So, again I go back, erase, okay, write that term. So, you will have CQ0 plus, this is sigma over C 0 to 1 omega r square half rho u square C, you got u bar over u t bar, okay, C d r bar d r bar, C d 0, sorry, okay. This is CQ 0, then plus, maybe I can put a okay, plus sigma over C, okay, I will write again 0 to 1, you have a factor mu, mu is there, again this will be multiplied by 1 over rho omega r whole square half rho u square C u bar by u t bar, okay, C d 0 sin psi d r bar. This is the CH naught term. Okay. Now, what you do is you combine both of them. Here you will have mu sin psi, okay, and you can now make it in a different form, that is I will write it sigma, you take out C d as though it is a constant, I am taking it C d naught, sigma C d naught, okay, and there is a half is there. So, I am taking that half outside 0 to 1. Okay. You know that rho and rho will cancel, this is u bar, this is u bar, because u square over omega r square is u bar square. So, this will become u bar cube. Okay. So, I am going to write it as r bar u bar cube over u t bar plus here also mu sin psi again u bar cube over u t bar. Okay. All right. Now, you know that is u bar cube only. So, this entire term will become, I erase completely here and write it as sigma C d 0 over 2 integral 0 to 1 u bar cube. Now, what is that we are going to put for u bar? U bar is the resultant flow. Now, I am saying my inflow is very small. So, u bar is almost u t bar. Okay. Then u t bar, if I say u bar is u t bar, that is nothing but what? Whole cube d r bar. Okay. And if you integrate and then take the mean value means 0 to 2 pi, you do it. If you do the mean value, you will get sigma C d over 8 1 plus 3 mean value, this is mean, okay, because you have to take the cube, because r bar cube, this will be power 4 1 by 4, okay, that 4 only, that becomes 4 into 2, that becomes 8, and then anything which has a sin psi, integral sin psi over the 0 to 2 pi, that value is 0, then sin 2 psi or cosine 2 psi, that is also 0. So, only thing is when you go to square term, you will write sin square psi is 1 minus cos 2 psi, something like that. Then you do the mean value, you will find this is the quantity sigma C d over 8 3 mu square, exactly it will come. So, you will find your C p or C q is integral lambda d c t plus sigma C d over 8 1 plus 3 mu square minus mu C h. Okay. But now, let us go back and then do some more adjustment, and you see that expression will become, because mu C h is still hanging there. Okay. So, what is done is, now what I am going to draw is related to flight dynamics. Okay. It is related to flight. What is my lambda? Lambda is mu, go back to your notes, lambda I. This is the induced, this is due to the forward speed, okay, in the hub, mu tan alpha plus lambda I. You look back your notes. Let us now draw a diagram. This is an interesting diagram. This is my hub. Okay. Hub is inclined at an angle. So, I will say this is my horizontal. So, this is my vertical, and this is the velocity is coming in this angle. This is horizontal, horizon. Now, this angle is alpha, because we know as per our definition, this is the hub. So, I will say hub plane. Okay. So, this is my velocity, oncoming velocity with respect to hub plane v cosine alpha, that is how I define my mu. Okay. Now, my thrust is given normal to the hub, and this is my H force. H is, and because the helicopter is flying like this, okay, this is the H, and weight of the helicopter, and there is a drag force on the helicopter. Weight of the helicopter is down, okay, and the drag force is along V. So, I am putting this is drag on the helicopter. Okay. Now, I am going to call this as theta f p, flight path angle. Okay. This is the flight path, and this is alpha minus theta f p. Okay. Because the tilt is only that much. Now, let us write our equilibrium equation. Equilibrium means because thrust and H force, they are generated by the rotor system, okay, whereas the weight and the drag, they are coming because of the fuselage getting dragged. So, let us write the equilibrium in the vertical direction T cosine theta f p plus H sine okay. This is equal to W plus D sine theta f p. Okay. And then in the horizontal direction you will have T sine alpha minus theta f p minus H cosine alpha minus theta f p equals D cosine theta f p. Okay. This is from equilibrium. All right. Now, I am going to make lot of assumptions. Okay. The assumption is these angles are small. Okay. Now, what I am going to make is these angles are small, okay, and thrust force is large, H is small. Okay. When I make that, from this equation, drag is also small, this is also small. So, I am writing here T is approximately W from this equation. Okay. Now, from this equation, T into alpha minus theta f p this is cosine. So, these angles I assume small. So, this is h plus d. I am just taking h that side. Okay. This is this equation. Now, I will write alpha minus theta f p is h over t plus d over t, or in other words alpha is theta f p plus h is non-dimensional, I am putting C h over C t. Here it is, I am writing it, t is w. So, I am putting d over w, just a algebra modification. Okay. Yeah. Now, here I will write it alpha is small. So, mu alpha. So, mu alpha plus lambda I approximately. For alpha I am going to write that expression, okay, which is mu times theta f p plus C h over C t plus d over w plus lambda I. Okay. All right. Now, I am defining my climb velocity. What is v climb? Velocity of climb, that is theta, sorry not theta, v sin, right, that is the climb velocity, which I call it V c. Okay. Non-dimensional, if I want lambda climb, that is I call it lambda c, which is this divided by over, okay, v over omega r, I am writing it as mu, theta f p is, okay, approximation. All right. Now, let us go back here and our equation this becomes, so maybe it is not necessary, now I can erase this part. Okay. Our lambda I defined as mu theta f p. Mu theta f p is basically non-dimensional lambda c. So, that will become lambda c, there is a lambda I. So, lambda I, then plus mu C h over C t plus mu d over w. Okay. Now, I go back, put it here. If I am assuming lambda, if I say it is a constant over the disk, this is nothing but C p will become lambda C t, right, and I have the expression here. So, I will write C p which is equal to C q, which is equal to lambda C t, and lambda I am writing all these things. So, I will have lambda I C t, climb velocity. Suppose if you do not want to do all those things, no, I do not want to substitute, I will keep climb velocity, because I can substitute for lambda this entire expression. I may say lambda I may be varying, but rest of them are all constant for the vehicle. So, I can directly substitute here, okay. In which case I can put lambda I dCt separately, but lambda C Ct, that is lambda C Ct, this is a constant, then I will have mu Ch, that is anyway coefficient. So, Ct and Ct will go off, plus you will have mu Ch, then this will be, that is again mu d over W, and you will have a Ct. So, I will write that expression mu plus mu d over W Ct minus, you still have that mu Ch term. So, minus mu Ch. So, you find minus mu Ch and plus mu Ch will cancel out. Okay. And leaving behind just 1, 2, 3, and then where is that? This is the another term, that is plus sigma C d naught over 8 1 plus 3 mu square. So, I have 4 terms, 1, 2, 3 and 4. So, I call my power, now I write everything in power expression. Power is Cp I induced, power due to induced, then Cp C power for climb, and then plus this term I write 4th term, which is Cp, this is due to the drag of the helicopter. So, I call it parasite drag, Cp maybe parasite, okay, plus Cp profile, okay. So, you have power for 4 terms, and each one of them you have the expression, if lambda is constant, you know you can get a lambda I at high speed, okay. The approximation is Ct by 2 mu, okay, for mu greater than 0.1. Non-uniform inflow is there. So, put some factor. So, you will get Ct square over 2 mu, that is the induced power. Climb power lambda C Ct, okay. And then this power you will now write it in a different form. See, how do you write the fuselage drag? Fuselage drag, you are writing Cp parasite as mu d over W Ct, okay. Mu is, you take it approximately E over omega r. Drag force is drag force divided by W and thrust, they are approximately. So, you will have thrust is, this is Ct, right. So, T and W rho pi r square omega r whole square, okay. This is approximately, because thrust is W. So, you will have V drag rho pi r square omega r whole cube. Drag force on the fuselage, you normally write it as whole cube, right, yeah, whole cube. drag force you write it as half rho v square some frontal area, please understand I am using the word frontal area of some body into a CD fuselage, some drag coefficient. Okay. Now, if you cancel out, because V over omega r, one of the omega r you will get it, because you know that V over omega r, this is V cube, omega r cube, that will be, I am writing it as approximately mu cube. So, but there is a factor half is there, half mu cube f c d over pi r square. Okay. But how they usually represent this as, okay, assume that C D f is 1, okay, find out the equivalent area, frontal area. You follow what I am saying? Do not, so normally wind tunnel they will put the fuselage, they will get the drag force, then find the equivalent F for C D equals 1. Okay. Since this is anonymous, this entire factor they take it as simply half, I think, mu cube F over A, that is all. A is the rotor area. Usually this factor F over A is of the order 0.01. It may be slightly more, 0.01213, something like that, F over A. That means this is the fuselage frontal area over the rotor disc area. Okay. Now you have the expressions for all of them. If you combine everything, so you have Cp, this term, plus sigma, okay, that is half mu cube F over A plus sigma C D 0 over 8 1 plus 3 mu square. This is the power. But please understand, there is another little bit more involved derivation. If you want to take radial flow and then reverse flow, okay, and because of the radial flow, that is the skewed flow, what happens to the drag? If you take all those, this factor 3 is modified to 4.6, that is all. But I will not go into the details of that derivation. Okay. Because again you make those assumptions, because this is a skewed flow, it is like a flow over a swept wing, and then try to get the equivalent value. Okay. After that you do the same integration, take an average, and it will come to, instead of 3 it becomes 4.6, that is again some approximation. Now you have your complete power. Now you see, that is why the fuselage drag is actually cubic to the forward speed. So as you increase the speed, that power will tremendously go up. So the power curve that day we drew, even if it is not climbing, so you will have your, so you can use this expression instead of getting CQ. Okay. For power expression you can directly use this, okay, for your computation or anything, because this is slightly better in the sense it gives a clean. So it goes like this. Okay. This is power versus velocity. There is a minimum, and we drew for range, maximizing the range, you go. This is the velocity, this is the minimum, this is the slope p over v wherever it meets, that velocity is for maximum range. Okay. Power available may be here. There is also another point which gives me optimum climb angle. Okay. What angle, what velocity if you fly, I will be climbing in the night, because if you want to clear something, the distance to that height. So, that is again the power available to P, that is drawn like this point. You will know the slope, this is Pt minus P, this is V climb. So, slope of that, okay, is basically the tangent of that curve. See, if you draw, that comes from this expression. You take a function which is Pt minus P you want this to be what? Good glide angle, that because you want to have minimum power, but not zero velocity. You want to have that angle of climb is good such that this is Vc, this is V, right. So, the power is available is directly related to how much climb velocity you can have. Okay, but you may say that okay, here I have lot of power, but your velocity here is large. Okay. So, the angle will be, that is why they call it as a nice word, that is a glide angle or something like that. Glide, not glide angle, it is the best climb angle. Okay, climb angle. Okay, best climb angle. If you want to maximize, that is what will you do? V du minus u dv. When you do that, you will have V minus dp by dv, because power is a function of velocity, power available is fixed. Then V du minus u dv, that is into Pt minus P over this, you set it 0. So, you will get dp by dv minus sign is actually Pt minus P over V. So, the slope of this curve, because the minus sign automatically this is a negative slope. Okay. So, this is Pt minus P, this is V. Okay. I will put it instead of Vc, this is V. Okay. So, this is the best climb angle, this is the best range, this is the minimum power velocity. So, at this velocity if you fly, you will cover more distance. If you go this way, you have longer flight time. So, you can call it maybe C, I think A, B. So, V A min power, okay, long endurance, this is V B max range, and V C what is the best climb angle. Okay. Just power versus velocity curve, that is all. Okay. So, anything? They define it like the best climb angle, that is all. So, I say, because if you look at it, you may, if you are but please understand, do not use that expression when mu is 0. Okay. For mu is 0, take the derivation what we have earlier used, even though because we substituted lambda I, which is for mu greater than 0.1, you may take it even for 0.07 or something like that, okay, approximately. So, you have to be careful when you are using these expressions. Okay, that is why climb, when you say, oh, what is that, mu is 0, so it is going to have infinite power. When you go to hover, take the hover part. Okay. Now, there is one term which is left, which is the moment of the hub moments, in the sense in the pitch moment, roll moment. I think that I will do in the next class.